A piece of wire of resistance R is cut into 5 equal parts. These parts are then connected in parallel. If the equivalent resistance of this combination is R dash, then the ratio of R over R dash is, to start with, I have a wire of resistance R and it is cut into 5 equal parts. So this is my resistance R and it is now cut into 5 parts. Now if it is cut into 5 parts, each part will have resistance R by 5. Because the resistance is cut into 5 equal parts. Now we have to find the ratio of the resistance connected in series and in parallel. So if this entire resistance is connected in series, if we add up, the total resistance, you'll agree, is R. R in series will be R1 plus R2 plus R3 plus R4 plus R5, and this will be R by 5 into 5. So the resistance in series here will be R. Now if the same resistances are connected in parallel, what will we get? So this is now R by 5. All the 5 are now connected in parallel. Each of them is R by 5. And if they are connected in parallel, the resistance now is written as R dash. They've given here R dash, will be reciprocal 1 by R1 plus 1 by R2, 1 by R3, 1 by R4 plus 1 by R5. And this is R dash. So 1 over R dash is the one in parallel, will be, now you'll agree, will be 5 by R, R1, so 5 by R, 5 by R, 5 times reciprocal of, because we know R1 is R by 5, so 1 by R1 will be 5 by R. So 1 by R dash will be equal to 5 times 5 by R. So 1 by R dash equal to 25 by R, which means R over R dash equal to 25 by 1. So the answer for this, your R over R dash is 25 by 1. An electric bulb is rated 220 volts and 100 watts. When it is operated on 110 volt, the power consumed will be. So here is a bulb with voltage 220 volt, applied voltage is 220 volt, and when you supply it a voltage of 220, it gives you a power of 100 watts. In the next case, the same bulb, however now the voltage has dropped. So in this case, if 220 volts was given and the bulb lit with certain brightness, now the voltage has dropped to 110. You'll definitely agree that the brightness will also drop. It will be less bright now. So we need to find its new power. Now when voltage changes, the power also changes. But one thing remains same for the bulb. It's the same bulb. So the resistance in this case and the resistance in the second case will remain the same because it is the same bulb. So in the first case, let us find the resistance. And we use the formula power equal to V square over R. We know our power here is the power is 100 watts. Your V square is 220 square into 220, and the resistance we don't know. So the resistance will be 220 into 220, that is 220 square over power 100. We'll just leave it at this. Let's go to the next case. Now in the next case, the voltage has dropped to 110, And if the voltage is dropped, we see it even in our homes, the bulbs will now burn less brightly. It will give us less heat. So let us see now what is the power in this case. So we use the same formula, P equal to V square over R, where P we do not know, we need to find. Our V square now is 110, so 110 into 110. And the resistance we found out earlier. The earlier resistance was, we just write it R. So we have power equal to 110 into 110 divide by resistance. So power equal to 110 into 110 divide by, we know our resistance, we take it from the earlier, that is 220 into 220 over 100. So power equal to 110 into 110. The division make into multiplication, then you have 100 over 220 into 220, and then you cancel this out. Here you get power is 25 watts. So the answer here, our new power is 25 watts. So let us just examine this question. When the voltage became half, from 220 the voltage became 110. The power from 100 became 25. The power didn't become half, it became 1/4, although the voltage was half. The key takeaway from this sum is the resistance of the wire remains the same. So in the first case, with whatever information was given to us, we were given V and P. We found out R. Then in the next case also V was given. We knew R from the earlier sum. We found out P. Two conducting wires of the same material of equal lengths and equal diameters are first connected in series and then in parallel in a circuit across the same potential difference. The ratio of the heat produced in series and parallel combination would be, so we have two conducting wires of the same material and equal lengths and equal diameters first connected in series. So you have R, both connected in series. So in this case the resistance in series would be R plus R, and that would be 2R. Now we need to find the heat produced in series and parallel, the ratio of the heat produced in series and parallel. So we know the heat produced is given by the formula V square R T. So here we have heat produced in series would be V square, R is 2R, and T. We'll write this equation 1. Now the same two resistances are connected in parallel. So here the same resistances are connected in parallel, which means now the resistance, effective resistance in parallel, will be equal to 1 by R plus 1 by R. So 1 by R parallel will be equal to 2 by R. So the R parallel will be R by 2. And we know the formula for heat produced is V square over RT. So for parallel, the heat produced for parallel will be V square, your R by 2 into T. So here we will write, this would now work out 2 V square T over R. Now we need to find series over parallel. So the series is V square T over 2R divided by parallel, which is 2 V square T over R. So we have V square T over 2R, the division becomes multiplication, R over 2 V square T. Cancel this, your answer will be 1 by 4. So we see that when there is an application to this question, series over parallel, the heat produced in parallel is 1/4. So if I ask you the question, where is the heat produced more? Heat is produced more when appliances are connected in parallel. So if you have two sets of bulbs, here I have two bulbs. First, they are connected in series to the same voltage, say 220 volts, and here they are connected in the second case in parallel also to 220 volts. Would they burn with the same intensity? Would they glow with the same intensity? You will notice we have already seen that heat produced, or the power in series over heat produced in parallel, is 1/4, which means when they are in parallel they will burn with much more, 4 times more. They'll glow 4 times more. However, when they are in series, they will glow less. The glow will be less in series. So the bulbs will glow more when they are in parallel. They will be brighter. In series, they will glow less brightly because the ratio is 1:4. How many 176 ohm resistors in parallel are required to carry a 5 ampere on 220 volt line? So we'll say let the number of resistances let it be equal to n. We have n resistances of 176, which means our total resistance, say 1/R, will be 1/176 plus 1/176 plus 1 by how many times? N times. Why? Of course, we know what's the formula. 1/R equal to what? 1/R1 plus 1/R2 plus 1/R3 and so on, and each of our resistances is 176 ohms. So we have 1/R equal to n times 1/176. This is equation 1. But it is also given to us, that the circuit carries a current of 5 amperes and 220 volts. So we have current in the circuit 5 amperes and the voltage in the circuit 220 volts. So we can now use Ohm's law, V equal to IR, and find the resistance. So V is 220, I is 5, and this is R. So your R will be 220/5, which is equal to 44 ohms. In the equation 1, we've already calculated our R. We said 1/R equal to n/176. So R equal to 176/n. But we already know now that the R is 44. We calculated the R here, 44. So 44 equal to 176/n. So n equal to 176/44. And the answer here is 4 resistors. 4 resistors. So the circuit diagram would go this way. So I have 4 resistors, each of 176 ohms, 176 ohms, 176 ohms, and the voltage I apply is 220 volts. The current flowing through this circuit will be 5 amperes. Several electric bulbs designed to be used at 220 volts electric supply are rated at 100 watts. How many lamps can be connected in parallel with each other across the 2 wires of 220 if a maximum allowable current is 5 amperes? Let's take up the specification of each bulb. Each bulb is connected to 220 for one bulb. The potential difference 220 volts, rated at 10 watts. So power 10 watts. If we know power and we know voltage, we know P equal to VI. Let's substitute in this. So we have power 10, voltage 220. So the current I flowing to one bulb will be 10 over 220. So 1 over 22 amperes will be flowing through one bulb. We do not know how many bulbs are there. The question is, there are several bulbs. So let the number of bulbs be, say, n bulbs. They're all connected in parallel. So if I were to draw the diagram, it would be something like this. The second part of the sum says that if a maximum current of 5 amperes, so here we have a current of 5 amperes that comes in, we'll call it as I, and this 5 amperes now breaks up into n bulbs. We do not know how many bulbs. So we have I1, I2, I3, I4, and we do not know how many, IN. So the equation for this will be I equal to I1 plus I2 plus I3 Rn, because we do not know how many bulbs. But the total current we know is 5 amperes. So I'll write 5 equal to I1, I2, I3, In. So 5 equal to, I we know is 1 over 22. So 1 over 22 plus 1 over 22 n times. In each of the circuit there is 1 by 22 amperes flowing in each of these branches because there are n such bulbs. So we have 5 equal to n into 1 by 22. So n equal to 5 into 22. So n equal to 110 bulbs. So the number of bulbs in this full circuit is 110 bulbs. When these 110 bulbs are connected to a 220 volt battery, the current flowing is 5 amperes. A hot plate of an electric oven is connected to a 220 volt line, has two resistance coils A and B, each of 24 ohms resistance, which may be used separately, in series or in parallel. What are the currents in each case? So here I have two resistances, say A and B, each of 24 ohms, and they are connected in three different ways. First they are connected in series, first they are connected separately, then they are connected in series, and then they are connected in parallel. So we need to find the current in each case. So first we'll take up separately. Separately means there's one resistance here which is 24 ohms, which is then connected to a battery of 220 volts. So this is quite direct. Resistance 24 ohms, voltage 220 volts. We go up to our Ohm's law, V equal to IR, and then we have 220 equal to I into 24. So 220 over 24 equal to I. So that will be 9.2 amperes. So in this case, the current flowing when they are connected separately, here this current is 9.2 amperes. In the second case, they are connected in series. So in series means there is A 24 ohms and another A 24 ohms. So this is A with 24 ohms and this is another A, B with 24 ohms. This again connected to a battery. So the resistance in this case is R1 plus R2, so 24 plus 24. So resistance is 48. The voltage, of course, is the same, that is 220 volts. 220 volts. So we have V equal to IR, and V is 220. Your I we do not know, and the resistance is 48. So the current here is 220 over 48, and that works out to be 4.6 amperes is the current. So in this case, when they're connected in series, the current flowing now becomes 4.6 amperes. Now the third case is when they're connected in parallel. So here they're connected in parallel, 24 ohms and 24 ohms. So 1 by R equal to 1 by R1, which is 24, 1 by R2, which is 24. So 1 by R equal to 2 over 24, that is 1 over 12. So your R in this case is now 12 ohms. Again we use Ohm's law, V equal to IR, and the V is 220, I we do not know, and the R is 12. So 220 over 12 equal to I, and then the I comes now, current comes 18.3 amperes. So when they're connected in series, the current flowing here is 18.3 amperes. So you can notice something here. So these were the three cases. When separately connected, we found the current flowing was 9.2 amperes. When they were connected in series, the current flowing was 4.6 amperes, and now when they're in parallel, the current was 8.3 amperes. So the maximum current was when they were connected in parallel, because when you're connected in parallel, the resistance is minimum, is less. So the current becomes more. Compare the power used in a 2 ohm resistor in each of the following circuits. A 6 volt battery in series with 1 ohm, 2 ohms, 4 volt in parallel with 12 ohms, and 2 ohm resistors. So let's draw the two circuit diagrams. So in the first one, we have a 6 volt battery in series with 1 ohm and 2 ohm. So here is a 6 volt battery connected to 1 ohm and 2 ohm in series. Now to find the power in this case, we must know the current. To know the current, we must know the resistance. So the resistance for series is R1 plus R2. So resistance will be 1 plus 2, that is 3. So the total resistance in this case is 3 ohms. And we know the formula for power. The power is I square R. So when we substitute our values, power equal to I square, we need to find the current too. To find the current, we will do V equal to IR. We know the V in this circuit is 6. So I we need to find, and the R in this circuit we have found is 3. So I equal to 6 over 3. So I equal to 2 amperes. So here for the I we'll put 2 square, and the resistance we will put as 3. So the power in this case will be, the resistance is a mistake. The resistance is not 3. We have to find the power, which one? We have to find the power only of 2 ohms. So our resistance has to be 2 and not 3, because we have to, the question is to find the power of 2 ohms. So power is 8 watts. In the second case, we have a 4 volt battery in parallel with 12 ohms and 2 ohms. So I have a 4 volt battery connected to 12 ohms in parallel and 2 ohms in parallel. Now I have to find the power only for 2 ohms, and you know the formula for power here, we are going to use V square over R. Last time we used I square over R, now we'll use V square over R. Now we have to find the resistance only, we have to find the power only of 2 ohms. So for 2 ohms, our resistance is 2 ohms. The voltage for 2 ohms will be the voltage across these 2 points, which you know is 4 volts. Will be the same voltage as the battery. So the voltage will be 4 volts, and we do power equal to V square over R, which means power equal to your V is 4 into 4 and your R is 2. So your power here is 8 watts. 2 lamps rated 100 watt and 220 volts and other 60 watts and 220 volts are connected in parallel. So I have a bulb A, and this bulb A has a power of 100 watts and it has a voltage of 220 volts, and we know the formula P equal to VI, so we can find the I. Power 100, voltage 220 into I, so the I will be IA passing through bulb A will be 100 over 220, and I'll just keep it 10 over 22, or you can keep 5 over 11, that is current passing through bulb A. We have another bulb that is 60 watt 220 volts. So this we'll call bulb B, and in the bulb B the power is 60 watt, the voltage 220 volts, so you have P equal to VI, and put the values. You have 60 equal to 220 into I, and the I passing through bulb B is 60 over 220, on cancelling it's 6 over 22 passing to bulb B. Let me go ahead and draw the diagram now. So here is my bulb A and this is my bulb B. They are connected in parallel. The current passing through this bulb A here, this current passing through A is 10, we call it I1 or IA, and the current passing through this second bulb we'll call it as IB, and the main current here we'll call it as I. So when this main current now comes and flows at this point, it breaks up into 2. So I can say the I equal to IA plus IB, current passing through bulb A and current passing to bulb B. The current passing through bulb A we have seen is 10 over 22, and the current passing through B is 6 over 22. So the total current here will be 22, 10 plus 6. So the current passing will be 16 over 22 amperes. So the total current drawn here will be 16 over 22 amperes. Or we use a formula that I equal to I1 plus I2 in parallel. Which uses more energy, a 250 watt TV for 1 hour or 1200 watt toaster in 10 minutes? So first we have a TV working for 1 hour. So for TV our power is 250 watt and the time it works for is 1 hour, and we know the power is here we don't require the power, we require the energy. The energy is power into time. So energy for the TV is power is 250 times 1. So energy is 250 watt hour. Now the next appliance, we have a toaster for 10 minutes. So toaster, power here 1200 watts and the time is 10 minutes. But we are not going to work in minutes, we are working in hours. So we do 10 by 60 hour. So again we are finding energy. Energy is power into time. So here the energy will be 1200 into 10 over 60. And this works out to be 200 watt hour. So when you compare, this is 250 watt hour, 200 watt hour. So who consumes more? We see that the TV consumes more energy. An electric lamp 100 watts, a toaster 50 ohms, and a water filter with 500 are connected in parallel to a 220 volt source. What is the resistance of an electric iron connected to the same source that takes as much energy as all three appliances? And what is the current through it? So I have three appliances here. One is an electric lamp, which is 100 ohms. Then we have a toaster of 50 ohms, and we have a water filter of 500 ohms, all connected in parallel. Connected in parallel, we use the formula 1 by R equal to 1 by R1, 1 by R2, and 1 by R3. Remember, this is my R1, toaster R2, water filter R3, all connected in parallel. So 1 by R, 1 by 100, plus 1 by 50, plus 1 by 500. Now here the LCM, you will agree, will be 500. So this will be now 5 plus 10 plus 1. So 1 by R will be 16 over 500. So R equal to 500 by 16 ohms. So now in this circuit again we put Ohm's law, V equal to IR, and the voltage is 220. The current passing through the circuit we do not know, but we know the resistance of the circuit is 500 over 16. So the current passing through the circuit will be now 220 into 16 over 500. And I'm not going to reduce it, I'll keep it the same way. In the second part of the sum, what is the resistance of an electric iron? So now we are dealing with an electric iron. And for this electric iron, that takes as much current as the three appliances. The current is the same. So the current here also is 220 into 16 over 5. Just like this current, same current. And the voltage also is the same. V also is the same, that is 220 volts. So we need to find the resistance. Again, so V equal to IR, and substitute here. You have 220 equal to I is 220 into 16 over 5, and your resistance we need to find. So the resistance here will be 220 into 5 over 220 into 16. Here if you notice I made a mistake, there should be 500 here, which means it's not 5, this is 500, this is 500. So the resistance, so this is the resistance, we cancel this out, we'll get R equal to 500 over 16 ohms. That is the resistance of the electric iron.